we will talk about light source. Because light source, the feature of the light source will depend on what the spectrum composition of the light itself. There are many kind of light source. When we talk about the optical feature of the light source, it must be starting from the principle of the light source. How for the light source to create the light emission. When we talking about the light emission, the principle for the producing light, we have many kind of mechanism. Actually, it is different energy form transformation. For first one, in intending descent light, it is created light by thermal energy, from thermal energy. Okay? And these two gets discharged in the electroluminescence. The light is produced by electrical energy. And the photoluminous principle, it is the light created by another kind of light. So this is light create the other light. Most common example is the fluorescence light. Okay, and These two are transferred from chemical energy into photo energy. And today we focus on the thermal energy and the electrical energy transfer into photo energy. Okay. For electrical type, we have a most common use application are these four kind of light source. The first one in cadence light bulb. We have used this kind of bulb for more longer than 50 years. Okay. And the fluorescent lamp, these are transferred into LED light already. Maybe 5 years or 10 years ago, when you see the light tube, most of them are the fluorescent lamp. And for the car lamp, the front lamp for the car, we use HID, high intensity discharge lamp. Right now, the light source are made by solid state lighting, LED. Okay. Actually, the solid state lighting produced by also semiconductor technology. So the light source itself, the volume, the size can be reduced to very small. And for the emission layer material, we can categorize into three kind of subgroup. The first one is inorganic. So we call it the light emitting diode. The second one is organic type. So there is organic material there. It is OLED. The third one is produced by polymer. So the P is the polymer. PLED. Right now, the LED inorganic is dominant the most of the light source market. So why we use solid state lighting light source? Because less power consumption. 20 years ago, there is energy crisis, so people asking for reduce the power consumption. So we require the green energy, power saving, energy saving. Okay. And there are several advantages of the solid state lighting light source. One is tunable brightness. Conventional light source, the brightness are fixed and sometimes it's unstable. For example, the torch or the gas lamp, the brightness is not stable, so you usually see the flash can flicker. And the solid state lighting, the emission spectrum, the bandwidth is much narrow. as compared to the conventional light source. So for narrowband spectrum, it means more saturated color. So we easy to have vivid colors from the light source. And because the volume, the size of the light source become very small, so we can more flexible the light pattern design and also the luminaire structure. We can make the light source from a small point or a linear line or curvature, or some curved surface. So many very diverse application for a light source has been created. And why we need to talk about the light source? Because we must understand the feature or characteristic of each kind of light source. Because we need to do the measurement, right? The emission spectrum is diverse. Then you need to take care about the method, how to measure the light factor. So in nature, in daytime, we used to apply the sunlight. Later we will talk about more about the sunlight. During the night, people use the moonlight. Okay. But right now we have artificial light source, so the moonlight has not so many applications. Right? So this is fluorescent light lamp, and this is the bulb, okay? LED lights. You must take care about the difference between the natural light source and the artificial light source. One is the spectrum composition are different to each other. The other one is the brightness level. Okay, the sunlight, the brightness level of the sunlight is much higher than common artificial light source. The other important factor is the size. So it will create a different kind of the view angle. So when you measure the light source, the view angle will create a different measurement result, right? And also the geometry factor are different, okay? Okay, next we will talk about the detail about the every light source. When we talk about optical waves, so we more focus on the spectrum. For the CIE organization, the International Standard Organization, they have defined they have defined 7 different type of so-called standardized source. Standardized source. Why we need a standardized source? When we doing the photo measurement, we need to compare and doing the characterization, calibration. When doing the calibration, we need a standardized source for comparison. So we need to do the standardized source. So first subgroup is standard illuminant A type. Okay. Later we talk about it is created by black body radiation. So we will see the detail why the spectrum will form in this way. Okay, and this tool right now we don't use this tool. Right now it is invalid. Previously, the CIE defined the skylight by average. Different time, different angle, view angle, the skylight average to have the 2 type of standard light source. Okay. Standard illuminant B, we don't use anymore, but the standard illuminant C still exists in some quantity measurement. It depends on the standard illuminant C. Next will be standard D. D means daylight. Okay, so daylight. What is daylight? It is black body radiation emission from the sun, and when go to the Earth, our Earth, the sunlight. Actually, the spectrum is smooth spectrum, but after pass through the atmosphere, many different kind of the air molecule will absorb special wavelengths. So when we see on the ground, okay, our daylight spectrum become with lots of discontinuity. So the black body radiation from the sun with this kind of smooth spectrum, when pass through the atmosphere, the air, the gas will absorb different spatial wavelengths. So when we see the light on the ground, will become the smooth spectrum become the discontinuity. Okay. For example, about 680 nanometer. There is one water molecule will absorb the photon energy. So here you will see lower density because absorbed by the water molecule in the air. For longer wavelengths, some absorbed by carbon dioxide, right? Some other different kind of atomic bomb. So the smooth one is black body radiation. So it is kind of illuminated A, but with the many kind of spike and the discontinuity, it is daylight. Okay. So we have a standard illuminated D. Okay. Later we will talk about the detail. This is another example. Show more narrow band absorbed by different kind of molecules. Okay. So let's see the three standard illuminants, the spectrum within the visible band. Because we talk about the photo energy. So actually, we more interested at the human eye can perceive. So within the visible band. So this spectrum is standard illuminant C. Okay. And blue one is the D50, and the purple one is D65. What's the meaning of the numbers after the D light? 65 or 50. Actually, it means 6,500 K. The 50 means 5,000 K. K means the unit of Kelvin, the temperature. Okay. So we use apply the temperature concept of temperature to describe the different distribution of the one series light source. Okay. Why we use the temperature? We need to go back to talk about black body radiation. I'm not sure right now. Do you have any experience about this kind of, for example, the iron bar? If is heated when the temperature increase from low to high, you will see the color or the brightness of the iron bar will increase. So when the temperature is still low, you will see start to see the iron bar emission the light. The light look like reddish in red color. Then the temperature increase more. You will see the light become from red turn into orange, yellow, then go to the white, then go to bluish. So the sequence when temperature of the iron bar increase actually about 1,050 K. Okay. 8,000 K, for example. From this range, the real temperature of the iron bar, and you will see the light. Lower when temperature is lesser, you won't see the light emission. After the temperature is over than around 1,500 K, you will see the iron bar become have some light emission. Okay, so the temperature in physical material, it will create and change the light brightness level and the colors. You will see around this low temperature, it is in red color. When the temperature increase, you will see the red turn into orange, and turn into yellow, and turn into white, and turn into become bluish. Okay. So it is a basic and common phenomenon for every material. Okay, so the color relate to real temperature. Okay. And this phenomenon has been discovered by theoretical research. By Planck. Okay, by Planck, he derived the formula to describe the emission spectrum. So we have a wavelength and the temperature and the some constant together. So he derived this formula, and this formula has very high accurate to describe the light spectrum. Okay. So how the story tells. Sorry, later. Hold on. Let me finish the category first. C, D, E, F, L. Okay. We have talked about this is daylight, right? So and what is E? E is a group standard illuminated B. This is a theoretical virtual light source. E means equal energy. So the spectrum within visible band has flat top. So there is no natural light source. Each spectrum looks like this. So it is theoretical, not a real light source. But because the spectrum has some feature, so sometimes we use it as a comparison source. Okay, so standard illuminated E, the spectrum is flat top for every wavelength has equal energy distribution. Okay. So for this kind of light source, when we doing the colorimetry or photometry quantity calculation, so first we have the tri-stimulus value equal to K to integrate within the visible band range, and equal energy times the color matching function. Because it is equal energy, so it become a constant. Right? So it can be removed out to the integral. So actually, due to the equal energy distribution, so it is a special corresponding tri-stimulus value, like so for the tri-stimulus value for the equal energy will be all the same. And such that for this special light source, the chromaticity will become 1/3 and 1/3. So this is a special point in the chromaticity diagram. Okay, let me see. So for the chromaticity diagram, we will see 1/3. 1/3 is about this one. 1/3. So actually, the equal energy, the corresponding chromaticity, locate at the center of this diagram. Okay, the geometry center. Okay. So this is a special point. Sometimes we doing the calorimetry calibration, we will compare to this kind of special light source. Okay, so E standard illuminated, E means equal energy, and the corresponding chromaticity will be 1/3 and 1/3. And next, F. What is F? Fluorescence. Why fluorescent lamp become one kind of standard light source? Because it's popular and less costly. Less cost. So it is easy to have this kind of light source. So for the CIE, they ever define. Okay. Yeah. Actually, the standard illuminated F. There are actually 12 different kinds of fluorescent light, and the spectrum has different shape, different composition. But the feature you will see, there are some fixed spike at some certain wavelengths, because they use the same energy level transition between some special molecules, ions. So the emission wavelengths will fix at the certain wavelengths. Okay, so this kind of feature of the fluorescent lamp, there are many spikes. This kind of spike with very high intensity, but with very narrow bandwidth, so it is not easy to calculate or not easy to measurement, or for calibration. Okay, but it is easy to obtain this kind of light source. So we use this special spectral distribution for one of the calibration or standard light source. Okay. So we have 12 different kind of light source. And part of them, for example, the F2 and F11, almost the same, except the F2 with some broadband background. Okay, broadband. So it is not purely from the fluorescence light. It is with some phosphor re-emission. So it is combination with the photoluminescence. Okay. And F11 is narrowband fluorescence. So it's more pure fluorescence light. All the spectral data, again, you can find. Remember, I introduced you at the CIE Open Data Set. Open access data set. Okay. So you can find the basic data here. This one for data, and the data we will see. The illuminance D55 and the D75 and HID, high pressure, and typical fluorescence depth. So this is the standard illuminant F series because we have 12 different kind of fluorescent light. Here is another data. Yes, so you still can find the another standard illuminant spectral data. Okay. I want to show you the data I've ever downloaded already. Okay, should be this one. Okay, this is F1. Okay, F1. You can find the data on the website, and this is F2. So you will see, except in addition to the feature spike, the F1 and F2 is more broadband background. So what's the difference, the background, with the background or without the background? So this is F3. And you can think about it, how to describe the difference between these light source. How to say it is brighter, or it is reddish, bluish, or color difference, brightness difference, or any method to describe, or any index to describe the difference between this kind of light source. Just because the spectral composition difference. How to describe the difference, okay? This is F4, this is F5, F6. So you see the spikes at the same wavelength, but the background mixed with a different kind of phosphor. So the background, narrowband background are different. Okay. So this is F7. And for F7, you will see the background become more flat. Okay. More flat. And what's the difference? What's the difference? Can you expect what's the difference, or what's the different illuminant result due to these two light sources? What's the effect? If we like to buy light source and you have two choice, which one you will select? You will select which one and why? This is F8. Okay. So F7, F8, and F9. There is a tendency of the background from the slope from positive slope is 0 and become negative, right? So how to describe the effect? And 10 become narrowband, 11 still narrowband, and 12 still narrowband. Okay? So this For standard illuminated F, there are 12 different kinds of standard fluorescent. And you can download the data, so you will see. No, I should not open this. So when you download the data, must be careful. The spacing in the spectral dimension is spaced with 5 nanometer, not just only 1 nanometer. It is because the measurement technology was limited by this kind of resolution, spectral resolution in that time. Okay, and it is kind of a style or habit. When you dealing some measurement data or raw data, you must recording the measurement condition at the beginning. Okay, not just simple measurement numbers. You must take care of the measurement condition, measurement quantity, the name. Okay, here the name and the unit. Okay, or some scale. You must recording all the detail at the beginning. Then starting to recording the measurement numbers. Otherwise, after 1 month or 3 months, nobody know what the number is. Okay. So if you go on the website to download the data, you will see it like this. So actually you will see F1 to F6 are called standard type, and the 7 to 9 is broadband. So remember there are more broad background in the spectrum. And the last 3 are narrow type, so just only several spikes only, without a broadband background. So what's the difference? When or in what kind of application we will apply which one standardized source, and how to describe in more easier way to talk about difference between these 12 light source, or even the difference between FDA more big difference. Okay, how to describe it? The last one will be standard light source L. What's the L? It means LED. This is a new light source, still under development. So people still study how to use LED light source as one of the standard light source. Okay. for the LED standard light source, people right now we still have no any common accepted model or functional form to describe the whole spectrum from the LED light. So we don't know how to compare or to do the exact calibration applying the LED light source. So we just can choose only one because it is easier to duplicate. People can buy the LED die. It is very stable and easy to attempt. So people can replicate this kind of light source. So right now we just say it reference spectrum, not say the standard spectrum. Standard like type A or type D. There is a very clear theory to tell you why the spectrum looks like this. Okay. So this is the standard illuminator A, the spectrum of standard A, and this is for standard daylight with 6,500 K. So this the blue one is the daylight, and the orange one is LED one. And the number, because in the beginning people just collect around 2,000 different kind of LED light source. So they have 2,000 different spectrum. So they do some statistics and give a very rough conclusion. And finally, the Osram, the company, the big company, jump into to say, okay, we select this spectrum, and I can provide this standard light bulb, standard LED. So if you like, if you want to have the standard reference spectrum, just buy my LED. Okay. So the number 41. Why is 41? It's not like the D65 or D50. This is tell you the temperature, right? But L41, 41 is nonsense because it's just a sequence number, ordering number in the first 2,000 collected sequence. So there is no special meaning for the 41. It is not like the temperature. No meaning, okay? Just 41. So this kind of spectrum, you can have a very clear idea. For this spike, this peak spectrum, it is come from LED, blue LED, and some part of this blue LED energy are absorbed by phosphor, and we emit the phosphor light. It is kind of a fluorescence light. Okay, so we have a blue and a yellow, so it looks like a white color for the spectrum. and you can easily to think about it based on your optical knowledge. You will see this kind of light source has obviously some disadvantage. For example, if you have a red color material like red apple, the fruit red apple, the longer wavelength, there is no many enough of energy can be reflected by the red apple. So the red apple under this kind of light source, it looks like very like dark red, not vivid red. So the red become black, more looks like black. So there is a big color shift. And also, for the green color material under this kind of light source, it will become looks like black because there is no many enough of energy, light energy, to illuminate on the material and can be reflected. Okay, so you never see this band of energy, so you won't see the colors. Okay. So right now we have 7 different kind of standard light source. Most of them are used for measurement, calibration, or comparison. Okay. If you have some photometry measurement device or calorimetry device, you look up into their specification data sheet. They will tell you the device when they sell to you before come out the factory. They will compare with the ASOS or D65. Okay, these two standardized light sources are more common use for device calibration. So, how accurate or the accuracy, precision of your device are based on these two standardized sources for calibration. You must think more about when you apply this kind of device into your experiment. You must think about do they provide so high accuracy again? Maybe not, because the light spectral composition may be not so good for your measurement materials. So you must do some comparison. So, based on our optical knowledge viewpoint, you will very easy to think about, okay, this light source is different from the others because the spectral composition are totally different, right? But for general application, spectral information is too complicated. Okay, when you go to the shop to buy some light tube or bulb for your family. You never tell the seller, I want this kind of spectrum, right? We will just say I need maybe 100 watt or 400 watt light tube, just one index. So we don't say the full spectrum or the spectral shape. It's too complicated. So how do we describe the light source itself? So we must think about it. How to describe the light source? First one, when we see the light directly, what kind of your feeling? Light color of the light is the first your perception, right? So how to describe the color of the light? We never see the chromaticity. We never tell the sellers, I want a light source with chromaticity of 1/3 and 1/3. It is impossible, right? Do you have any experience when you go to buy the light bulb, how to differentiate from the many kind of product? You just say yellow light or white light, just only two kind of selection, right? But what's the difference? What's the difference? If you read more about the label of the product, actually you can find the color temperature. They will say the color temperature. Switch. For example, we like to buy a bulb. You will select how many watt. How many watt means brightness. But it is a traditional way to describe how brightness you can have from this bulb by watt. The watt actually more precisely it tell you the electricity energy consumption, not the photo energy created. Okay, so how to describe the photo energy created? Remember we talked about the photometric quantity. We not use watt to describe how bright the human eye perceives. We use lumen, right? So we weighting by the lumen efficacy function to describe how bright we will perceive. So we go to the detail. They will tell you the temperature. Use temperature describe different kind of light color. And when you see the spec, what you can select? Natural light. Actually, they don't tell you too much because in the first beginning, actually the product is described by the numbers, but everyone go to ask the salesman what's the light looks like. Very few people can understand the meaning of the temperature, right? So the seller go back to change the communication way. So they just say it is yellow light, natural light, or white light. Okay? But actually the white light is not pure white light, kind of blue light. There is white light mixed with part of the blue light. So you will see the light looks like bluish, and this is yellow light. Okay. So we need to describe by quantity. So we use temperature to describe. But you never think about it. Your lamp installed in your house, when you turn on, their temperature becomes so high, right? The temperature, the luminaire, the light source, never have a real temperature go so high. 100 or 150 50 Celsius degree is high enough. Never go to 3000 K, 6500 K. Never go so high. So what's the meaning of the temperature? It is not the exact temperature concept again. So let me finish it. So how to choose the light source? The first one is how many watt it can consumption the electric energy, right? Actually, you more concerned about, they tell you the watts never equal to the brightness, lumen, okay? Okay, here, lumen. Actually, the bulb has 3500 lumen, but just 100 watt. So how many the conversion efficiency from watt, it is electricity energy watt, to photo energy lumen, right? So you can easily calculate what's the conversion efficiency. Conversion efficiency. We input 100 watt, create 3500 lumen. So we will have a 35 lumen per watt. Okay, for this light bulb. So if you like more power saving, energy saving, we should have a higher number of the conversion efficiency. Not just reduce the watt, because you need the lesser watts, but higher lumen, more lumen. Okay, right now you must have learned about the knowledge. The watt talk about power. So what's the power? We have a photo power, electricity power, chemical power, potential energy power, kinetic power, right? So right now we talk about the consumption power, and we want to have a brighter, more light energy, so we need more lumens. Okay. Okay, so this is detail of data sheet. They provide three kind of bulb, different energy consumption: 10 watt, 13, 16 watt. Right now, it is not the key issue. Okay, it just tell you roughly the light brightness table. Actually, we need to compare lumen. Higher lumens, it means more brighter. Okay. And the color temperature. What's the color temperature? We will talk about later. And what do you see? It is electric product. Also is kind of a photo product, right? So we have electricity feature, and we have photo features. This is the electric features. This is photo features. This is photo, geometry, photo, electric, mechanic. Okay. The lifetime is depend on which kind of method to measure the lifetime. They tell you 24,000 hours. How long how long you can expect when you buy this kind of bulb, go back to your home. Next time you need to change it. When will be the lifetime? 24,000 hours. How long it is? How long it is? Can you have any idea? 24,000 hours. How long it is? It is about 3 months, right? One day is 24 hours a day, and 30 days for 1 month, right? And if we have 4 months, no, 40 months, it means 24 times, so around 1,000, right? So around 40 months, 40 months around 3 years, 3.5 years. Okay. It means if you buy this bulb, go back to your home and turn it on, never turn off, you can last over 3 years. It's kind of long enough, right? So, which one? All the spec, right now you should understand the meaning. It's that the color temperature and the color rendering index. I will talking later. When you talk about light source, actually we use the color temperature and the color rendering index to describe the photometric property of the light source. Okay, we use color temperature and the color rendering to describe the property, photometry property of the light source. So we use more precisely, we use correlated color temperature to describe the color of the light. How white is the light source, okay? And use color rendering index, CRI, to describe how good the quality of the light source. What's the quality? What's the function of the light source, especially the 19 luminance? What's the function? We most care. We like to light up all the space we are in active in this space, and we like to see every object clearly, right? If we have if we use a bad light source, most of the object maybe looks like different color and different fit to our memory. so we don't understand what the object is. Okay, we will not easy to recognize every object in our environment. So we need a good quality of the light source to let all the object looks like the real case. So we need two index to describe the light source, how it is look like and how good it is. Okay, so how to define these two quantities such that we can use them to describe how it is how does it look like and how good it is. How does it look like? In our idea, we just only to say how bright it is and what kind of color it is, right? But for lighting light source, we want to see all the object. And based on your optical knowledge, our light source, we should emit the spectrum as broad as possible, such that our object, we use the reflectivity, spectral reflectivity, right? So we times reflectivity and the times color matching function. That's what we see to integrate. So the light source, spectrum of the light source, we expect their bandwidth must be as broad as possible, such that we can provide good enough energy for each kind of wavelength, such that it can reflect good enough of energy at any spectrum. Okay? So this one should be broader, is better than just only several narrow band spike. Right? So how to describe it? We need a broadband light source. For broadband light source, the color more looks like white. So what is white? The white means every wavelength has some energy. Okay? All the wavelengths have its own energy. So it is white. White means everything all together. We have everything. Okay? So actually for lighting light source, they are white color, in white color. But if we see into the chromatic diagram, this corner is red. This area region is orange and yellow, and this corner is green. This corner is blue. Okay, and here is cyan, purple, and magenta. So within the center, this is white. So white color, not just only one color. There is some widespread region. Every point is one kind of white. So we have many kind of white. So how to describe the different white? we use color temperature. Color temperature. Because we have the black body radiation in nature. Black body radiation means every kind of material, if they have the same temperature, then they will emit the same spectrum of the radiation, optical radiation. Okay? So no matter which kind of material is, if the temperature goes the same, the light emission spectrum will be the same. Okay? So we use this kind of nature light source help us to define which white and how to describe it. So back to the black body radiation. In the end of last century, the physicist Planck has derived the formula for black body radiation. Their spectrum will be proportional to inverse proportional to power 5 of wavelengths. Yeah. So don't pay any effort to remember this formula. Okay? Don't try to remember it. Except you need it every day, so you naturally will remember. Don't try to memorize this formula on purpose. Okay? C1, C2 are two constants. They are combination of some nature constant, speed of light, electron quantity, okay, and so-called Planck constant. So you will see the spectrum will be changed by the temperature. Okay? So if we change the temperature, we will have the spectrum change. Okay? This is low temperature, this is high temperature. The spectrum move from low temperature to high temperature. The peak wavelength will move from longer wavelength to shorter wavelength. Okay? Yeah. So this narrow range is our visible band. So if the light source has energy within this range, then we will see the light is turn up, is bright. So for black body radiation, when their temperature, real temperature of the object or the light source, okay, higher and higher, even higher to 1000 K, the emission, they have some emission, but we never see it is bright because the emission never come into our visible band. So our eye won't sense the emission light. Only after 500 K, there is little energy coming to our visible band from the longer wavelength side. So actually, we will start to see looks like in red color. That's why we see red color in low temperature, because the black body radiation spectrum coming to our visible band from the longer wavelength side coming to here. Okay, and when the temperature goes higher, 2000, so you will see more energy coming to our band, our visible band, but still higher energy in long wavelengths and low energy in short wavelengths. So it looks like red, orange, yellow. And when come to 5,000 and or between 5,000 to 7,000 K, the peak just coming to our visible band. So we will see more like the equal energy. Looks like an equal energy within our visible band. So we will feel when the light source with 5,000 K to 7,000 K, the color of light looks like more white, close to white, right? Because you see our visible band, within our visible band, the spectrum is more flat, more looks like equal energy. So the color of the light looks like white, very close to white. Okay. And when the temperature of the object goes higher than 7,000 K, you will see our visible band will become to the right side of the emission spectrum. So the slope will be changed. Okay. So the short wavelength region will have a higher energy than long wavelength region. So the spectral distribution become this kind of shape. So the color should be more bluish. You will look more blue color in the light, because the short wavelength region has higher energy, photo energy, right? So from this picture, you will see and you should understand why the previous example, the phenomena will happen in this sequence. When the iron bar temperature of the iron bar or the filament of the lamp, the temperature increase from low to high, you will see the color from red, orange, yellow to white to blue. Okay. And if you have any chance go to the higher mountain or some very dark region, you will see the starlight, right? Starlight, and you can try to see every different star. They have a different kind of color. Some star with color in red, orange. Some star with light with bluish. Okay. So right now you can easily understand when you see the blue star means on the surface of the star has higher temperature than the surface of the star with red colors. Okay, because it is the same principle, black body radiation. Any object, no matter what the composition or material it is, if they have the same temperature, they will emit same spectral emission. Okay? So same temperature, same spectrum, same colors. Okay? So be careful. We try to wide expand our concept based on black body radiation. This is a common, simple phenomenon. Okay, so based on black body radiation, we have a real temperature. We have the same corresponding spectrum, right? And so we see the same color of light. So right now you have a see, based on the black body radiation, we have a connect chromaticity quantity and the thermal quantity. We have a very tight connection, right? So why we say it is yellow light with 3000 K? Because 3000 K of black body radiation will emit this kind of spectrum, and it will be looks like yellow colors. Okay. So right now we have found, based on this nature phenomena, such that we have create tight connection between colorimetry quantity and the thermal quantity. So right now we will expand. We use temperature to describe the color, especially the white color. So in chromaticity diagram, right now we have a special light source, right? So in the chromaticity diagram, you can try by yourself, because right now you have this kind of formula. So you can assume to increase the under any given temperature, you will create a spectrum, right? You can easily calculate a spectrum. Fix the temperature, for example, 100 K. So you can give the wavelength from 380 to 780. Then you have this spectrum. And based on our calculation process, if you have any spectrum, then you can calculate the chromaticity coordinate, right? Remember the process. So right now you can change the temperature from 100 to, for example, 20,000. Okay. You can increase 500 or 100 per point. Then you will have lots of temperature. Right? For example, in the Excel spreadsheet, you can create 100, 200 to 20,000, and you will have the corresponding chromaticity, right? So you can calculate the value. So next step, you can draw the chromaticity onto the diagram. Then you will find, when you increase the temperature from low to high, you will see the corresponding chromaticity will form the locus like this way. Okay? And remember our white range is around this area. Okay? So the color temperature looks like a rule to tell you how white it is, because we use the temperature. So lower temperature is more close yellow, right? Higher temperature is close to the blue area. So if we apply the color temperature, so this kind of temperature no more the thermal temperature of the object. The temperature tell you the color, no more tell you the thermal temperature again. Okay? In the beginning, the temperature is the thermal temperature, but we, based on black body radiation, we connect the thermal temperature with the chromaticity coordinate. Okay? Now we expand the concept. So we use the temperature to tell you the color. So this kind of temperature no more tell you the thermal concept. Instead, it tell you the calorimetry concept. So we say this kind of temperature become color temperature. The color temperature just tell you the location on the locus. Okay? So lower temperature means close the yellow or red. Higher temperature just tell you more close to blue colors. Okay? So in this concept, the thermal temperature become color temperature. The temperature quantity just tell you the color information, no more tell you thermal information. Okay? After the black body radiation transfer, the temperature just tell you the calorimetry information just based on the diagram. So you will see lower temperature tell you the color of light is more close yellow. So we just see the website of product. It tell you 3000 K is yellow light, right? For 6000 and 500 K is close blue light. So it is more bluish. This is yellowish. Okay. So remember, color temperature just tell you on the locus where the location it is. So tell you which white it is. For lower color temperature, the color will be more close to yellow. For higher temperature, this kind of white is more bluish with more blue. Okay? Higher temperature will be more blue composition. Okay? Understand? So right now we have a color temperature. So must remember the color temperature because based on the black body radiation. So all the exact definition with color temperature only talking about the point, only point on the locus. If we like to talk about deviate from the locus, for example, this area, it is still kind of white, but there is not exact locus located on the locus. This line, this curve, we say it is black body radiation locus. Okay, so it is calculated from low temperature to temperature to obtain the corresponding spectrum and calculate the corresponding chromaticity, and we plot on the diagram. So create this kind of special locus. And about 2,000 or 20,000 or 25,000, the chromaticity will look like stop limit here, no more close to blue region. Okay, so it is not uniform. This is not uniform with the temperature. So you can calculate by yourself. Okay? To check this kind of phenomenon. Okay, then we can transform from thermal temperature into color temperature. So thermal temperature just tell you how high the temperature when you touch it, you will feel the temperature. And the color temperature just tell you when you see the light directly, you will see the color. What color you will perceive? Okay, you will feel the color of the light. So the color temperature tell you color, thermal temperature tell you the thermal information. Must be differential from each other. You never see all of them, all are colors, all are temperatures. So we say the same thing. No, we use temperature in different fields, so they have a different meaning. Okay, so you must differentiate very clearly. Okay, next, when we talk about other white, never locate on the locus. How to say it? We apply the geometry concept to help us to describe more other white. Okay. So let's say we have a baseline. Black body radiation locus here. So actually there is a spatial scale on it. It's a thermal color temperature, right? So we have a color temperature as a scale on the curve, the curve. So when we have some other light source with the different spectrum and create a different color coordinate, for example here, how to describe use the same similar color temperature concept? We will think about it. It is kind of white. It is still a white color. So how to apply the color temperature concept to describe this kind of white? How to describe it? We use the concept as a geometry method. Okay, so we try to apply. We compare every kind of white on the locus to the target colors. So we can calculate the distance between them, right? So which one we will choose? We like to find one point with a short distance. It means the short distance means the color difference is small. So these two colors will be looks like each other, most like to each other, right? It means this color and this color looks like very similar to each other as compared to other point, right? So which point has the shortest distance? Has the shortest distance with it? Based on your geometry knowledge. If we draw the tangent curve at this point, so this tangent line with the connection line, they should be orthogonal to each other, right? So based on this condition, we can easily find the corresponding point such that it is most close to our target colors. So these two colors is most similar to each other. So we say if this is with color temperature to describe this point, and we apply the orthogonal condition. So we have this color close to this one. So when this concept applied to this color, we say correlated color temperature. So it is correlated, means close to that point. So the color most like to that point. Okay, most like each other. So it is color correlated color temperature. Correlated. Okay. Correlated means the chromaticity is not located exactly on the gravity radiation locus. So in this right now we have a so-called isothermal isotemperature, isothermal. No. Right now we say iso-CCT. So we have this kind of lines. So every chromaticity point coordinate on the same iso-CCT lines, it will be has same CCT. Okay? So it's the same CCT. So we just expand the linear scale to wider range. Okay? So actually the CCT just only one dimension scale to describe your white, which kind of white it is. It's more yellowish or more bluish. Just tell you use the lower CCT or higher CCT to exactly describe your color of light. Okay? So this is CCT concept. So we follow different quantity, different concept to help us to define the color quantity, color property. Okay? So right now we have a CCT, correlated color temperature. We apply geometry concept, thermal concept, and gravity radiation principle. All of them combined together, we have a correlated color temperature. Okay? So most of the time when you see the product sheet tell you the color temperature, actually it is correlated color temperature, not color temperature. Okay? Because color temperature only tell you all the point exactly on the gravity radiation locus. If we talking about some deviate from the locus, you must use correct color temperature. Okay, it means this kind of color of light is more similar to that temperature, color temperature of light. Okay, more looks like to that temperature of color temperature of light. Okay, so we have the first index to describe the light property, how white it is. Okay, how white it is. Okay. So it is Planck radiator. Sometimes the black body radiation has been explained by Planck theory. So we will say, sometimes we will say there is a Planckian radiator. Okay, Planckian radiator. So it is talk about how white it is. But the white, low CCD white or high CCD white, it is not exactly determine the quality of the light source. Because we need to shine, turn on the every object, help you have a good looking, right? So we need another method to test how good, what is the quality of the light source. So we want to have a good light source such that if we have many kinds of object, okay, for example, red object, orange, yellow, green, cyan, blue, purple, and there are many different colors between them. Okay, so if we have a light source shining on different color of object, can we create exactly the color it is or not? It is our basic idea to test the quality of the light source. If we have a good quality of light source, actually we should have recover all colors, right? If the light source is not so good, maybe some color will be big shift, serious color shift. So maybe green color, it will look like a good orange or cyan, right? So how to test? If we have this idea, then we will know how to test it. CIE, they developed 14 object, standard object. 14 object. So based on your optical energy, optical knowledge, how to describe the object is more efficient. With more efficient, we just tell you the reflectivity, spectral reflectivity. It's good enough. If we have the spectral reflectivity, we will know this kind of object, light source shining on this object will reflect some spectrum of light, and we can test the spectrum of light will induce what the corresponding color coordinate. Then we have a standard. Because this is standard object, so we have a spectral reflectivity and also has small standard, has a standard chromaticity. So when applying a testing light source shining on this object, we will create some color measure, color chromaticity. So we can compare how big is the data, the color shift. Then we will know how good is the light quality, right? Understand the idea? The idea is clear to you. So next we will talk about the color render. Color render. This is color render. If your light source has good color rendering capability, you will recover all the color of every object exactly. Okay. For example, we have the same object under different light source. So you will see the red or blue or white become different feeling, right? And same fruit under different light source. So which one is better to you? These two may be good to you because you can identify each object clearly. But for this one, you almost cannot identify which object is which kind of fruit, right? So this is bad quality of the light source. This is good. The other example is use flower because flower has more diversity of colors. The other one, we like to use female model of their skin, okay? Because it's not just color itself, it also relates to human daily memory. We every day, every time see the skin color. The skin color is kind of very complicated, not just one color. So we like to use flower or female model to test how good is the light source. So you can see for bad light source, the flower just look grayish, right? Grayish. And if you have a good quality of colors, light source, you will see every color of the flower, right? So you can see this flower, the same flower, looks like grayish, orange, yellowish. Actually, it is red, fresh red. Okay. So, based on our idea, we have designed one index to test based on this concept. To test, give you one index to tell you how good is the light quality. For this one, the CRI color rendering index just 60. So we design one good index is range from 0 to 100. So you will feel the quality is good when the index more close to 100, right? So this one is better. The CRI is 80. This is most best. This is the best light quality. So the color rendering index is 90. Okay. Right now, our LED light source, it is very easily to have a CRI, create a CRI higher than 80. 75 is the lowest level. Okay, 75 is the lowest level for LED with blue LED dye combined with yellow phosphor. This kind of feature construction, we will easily to have a higher than 75 of CRI. Okay. And if you have a good design of the phosphor, and it is easily to have a CRI higher to 95, 98, but actually you will pay more effort and with higher cost. Okay. So right now, when you try to go to the light shop to buy some bulb or some light tube for your family, you should understand which room in our house to use this light source. Okay, in your living room, what kind of light source you will need? You need bright, right? And maybe you need to some focus of your status. So usually in living room we will have a higher lumens, and so the CCT should be high CCT, okay, higher than 4,000K in your living room, and maybe 3 to 5,000 lumen it should be with this distance. Actually, we need to calculate the illuminance, not just the luminance. And the CRI, actually in your living room, maybe higher than 80 is good enough. Okay. And for your bedroom, you need help you to have an easy move, emotion to relax. So actually, we will choose lower temperature, color temperature. For example, 3,000K, yellow light. It will help you to relax yourself. So your bedroom, we use low CCT. When applied in your study room, living room, we need focus, right? So we should choose higher CCT, okay? And in your dining room, you eat food, right? And for female, you may do the makeup on your dressing and your face. You need to see the color more exactly. So you should choose the CRI higher than 85 or 90, higher than this kind of CRI to use in your dining room or your bedroom with the makeup space. Okay? In the beginning, you have heard the Philips. Philips is a big company to create the worldwide company to create the light source. They first use three wavelengths of the light tube to create a white light, because our eyes, if we sense RGB 3 component, then we will see the white light. But actually, if you see the spectrum, it's not so simple. So in the beginning, the Philips manufactured the white light tube with three wavelengths. For example, the fluorescent light with a narrow band. And they failed. The product not so accepted, so good. What is the reason? Because when the people buy this kind of light source back to their home, installed in the dining room, all the food you cook, looks like this. Better quality, okay? Just light up, you can see the shape, but you cannot see the color. So you, all the effort pay on the cooking looks like that. So you don't like it. And every female, the effort on their makeup on their face or dressing looks like that. So the light bulb is not so good for selling. Then they know they should create high CRI color rendering. So they put more phosphor to create widen the background spectrum. So create the higher CRI. So again, we will see the hood or female makeup looks like this. Okay. So this is just for comparison. This is not the real thing. Okay. For the forehead part, actually we have 50 to 60 CRI. It means low CRI, such that you cannot see every color exactly, right? So if you see the skin looks like this, it is not good looking. Why? You will not see the detailed small blood vessel under the skin. So you cannot see the good healthy red in the skin, right? Because our light cannot recover that kind of red. Okay. So in the middle part, we have another light source with higher CRI. So it will become more healthy, looks like healthy. And the lips part, we shine with a better light source with CRI of 80 to 90, okay? Or even 90 to 100. So every color has recovered exactly. So you have to feel good, okay? So right now I try to give you a concept. How to simply describe a light source. One is use CCT to tell you the color information. When you directly see the light, okay? And the other index is CRI, tell you how good is the light quality. And we not see the light source directly. We see the illuminate result. We see the object. We check the color recover degree. Okay, how good the color recover. $20 years ago, the story is different. When the LED just come out, people will say, in Asia area, people looks like more like the low no. In Asia area, people looks like more like to see the white skin, right? People more like the white skin. So the high CCT light source is better for area Asia region area. Okay, and for Europe people, they live higher altitude, so they like to see more sun. So their skin preferred skin color is more brownish. So they more like the low temperature color light source. But 20 years after, right now, no such big difference. All white become the same. Okay, so we like natural color. The house designer or architecture, they will tell you prefer the 4000K natural white. They will suggest to use natural white. Okay. So this is 3 examples. Try to tell the difference between these 2 kind of index. Give you different feeling. So this is warm white, lower temperature and the lower CRI. So you cannot see the skin color so good. So you should try to see. Which face do you prefer? It depends on your preference. Okay? So this is higher CRI and higher CCT. This is higher CCT, CRI and low CCT. Okay? Someone prefer this one, someone prefer this one. And this one is for comparison because the same face, same skin, but this is for warm white, low CCT and low CRI. Low CRI. Okay. The exact difference is between, can you see the small blood vessel under the skin? Okay. Your skin white is kind of transparent, such that you can see the vessel under the skin. So you have a white mixing with red. You will look more healthy, and people prefer this kind of case. Okay. So this example just try to train you how to see these 2 kind of index, CCT and the CRI. They both used to describe the quality of light source, one light source. Okay. So how to calculate CCT? I have tell you how to calculate, right? Right? How to calculate CCT? Actually, there are several algorithms to calculate the CCT. It's not so easy, but the idea is easy. Try to find a point most close to your test color point, and use the corresponding color temperature as your represent color temperature. So it will become correlate color CCT, color temperature. Okay. If you like to have a program to calculate CCT, just come to me after the class, because we have maybe 4 methods to calculate. And lighting industry, they use some algorithm. The CCT is not so exact, but they has already learned very good experience to calculate by themselves. So if you apply another exact algorithm to calculate more correct CCT, they don't like, because they don't know the feeling. Okay. Next is CRI. How to calculate CRI? I just tell you the concept, right? So CRI has defined 8 color sample. So this is the standard color sample. They have ever prepared in the beginning when the standard announced. Right now, nobody knows how to have this kind of color sample. So CRI index, we never real measurement. We cannot measure the CRI. We only can analyze and by calculation to have the CRI. Okay? So in the beginning, they define this 8, and right now we explain to 15, 14, 15 different kind of color sample. So right now we only recording their spectral reflectivity. Okay, spectral reflectivity. So you can check this kind of spectral information on the OpenSS dataset, and they provide this kind of information. They give you 15 different kind of color sample of their spectral reflectivity. So if you have the spectral information and you measure the spectrum of the light source, then you can do in the calculation. Okay, how to do the calculation? We assume the light spectrum shining on the testing object. So two spectra multiply to each other to have the resulting reflecting spectrum, right? So each spectrum can calculate the corresponding chromaticity coordinate, right? So we test 8 color sample. So we have 8 colors. It is virtual measurement. We just calculate the spectrum. So we have a calculate color coordinate, and these 8 color testing sample can be test under the standard light source. For example, A source or D65. Some standard light source. So you have another standard 8 colors, right? So you calculate each color, the color difference based on a geometry concept. Just calculate the distance between 2 color coordinates. We use the color, the distance on the color coordinate to represent the color difference. Okay, so we have this kind of formula. So we have 8 sample and 2 light source. One is testing light source, the other is standard light source. So each light source shining on the 8 color sample. So we will create 8 different color coordinates. So we have 2 sets of 8 color coordinates, and each one can calculate their own color distance, color difference. Okay, so the coordinate distance to calculate the color difference. So we have 8 color sample. So just doing the average. So this is average color difference. Average color difference. So 8 color. So divided by 8. So this is average color difference. Average. And this is scale transformation. just try to make the best quality become 100. So if you recover every color exactly, so each color, each object has 0 color difference, right? 0 color difference. So you will have 100 as your result. So if you have no any color difference, you will have CRI over 100. Okay, so 100 means best quality. It means you can recover every colors exactly. Okay, if you have any color difference, the scale is 4.6. This is just experience constant, no theory base. We just want to make this kind of scale. Okay. So color difference, every color difference times by 0.6 scales, and try to see how good far from 100. So it will become how bad it is. So this method tell you the CRI based on 8 color samples. And this 8 color sample, actually it is not saturated color. It is not saturated color. Actually they are unsaturated color. Means not a vivid color. So we can see if we apply daylight on this testing sample, you can see every color exactly. So the CRI is 100. So this quality is good. Okay? No wonder. It must be 100. Why? Because daylight, it is standardized source also. So why it is 100? Because the result is compared with itself. So basically we have 2 light sources, right? One is testing, one is standard. But daylight, it is standardized source. So the testing light source and the standardized source are the same. So never have the color difference. So it must be 100. Okay. And for the standard illuminator A has the same case. For the illuminator A, it is kind of the standardized source for CRI calculation. So for standard illuminator A, the CRI must be 100. Okay. And if you testing on the metal halide light source, there are many spikes. So you will see the pink color and the blue color has big, serious color difference. And again, the cyan color looks like green. Okay, so the blue part disappear. Blue part disappear. Okay. And for the high pressure sodium light, CRI just only 25. Very low. Why? Because it's just only 2 meter wavelength span. So you cannot see the red, you cannot see the blue, right? So everything looks like the yellow because the wavelength is within this range. And the cool white light source, the CRI 58. Small background and a strong spike, right? So you can see the blue color disappear, and green color has some deviation, okay, and the pink and the red has some kind of a deviation. So when you learn a new index, you must understand their background principle and the measurement method, and you must take some time to learn the number and the effect or their meaning. You must compare with it. So the CRI, actually, the CRI is not accurate index. It means if the CRI difference within 5 is not so bad. I mean, if the CRI reference within 5, the quality is not so big difference. Okay, so it is a rough index. So we won't say 80 is better than 75, but it is better than 70. Okay, if the difference within 5 is almost the same. Okay. Okay, so for our common light source in the market, we can compare their CRI. In incandescent or halogen bulb, 100 again, white. Itself is the standard light source, so never have a color difference compared with itself. So it is always 100. So this kind of 100 is not represent it is good quality. Okay, because it is yellow light actually. And if you stay within the yellow environment, you will feel dizzy and sleepy, quickly fall asleep. Okay, because the yellow light help you to relax yourself. So this yellow light we like to have installed in the bedroom or bathroom. Yeah, rather like the flash light on the wall. And this is phosphorescence metal headlight. Fluorescent, okay. Lower than 50, they are not good for lighting light source because the color will be different, badly shifted. Okay. So there is a baseline. It depends on the application. If we need the light source for outdoor because you have natural light, help of natural light, so we require higher than 40 is good enough. Okay, 40. And outdoor for working area is better to 60. Okay, this is given by 25 years ago. So right now we have a good technology, and we can create a better light source. So easier to have a higher than 80. Okay, so in indoor retail, museum, or clothing shop, or dining restaurant, we need higher CRI. Okay. About 10 years ago, people think because the CI, everyone have learned how to treat this kind of index. We know 80 is good or not, 90 is better, right? But when we look back, every step of when you calculating the CI in our currently knowledge, every step is wrong. Every step is wrong. Why? Because this formula calculates the distance, geometry distance on the diagram to represent the color difference, right? But unfortunately, this color coordinate, color space is not uniform. It's absolutely not uniform. So it means the distance cannot represent the color difference. Exactly cannot represent the color difference. And the worst case is previously we used WV, not XYZ color space. This kind of color space we never use. They are abandoned, but just only used for calculate the CI. Never used in other application. So this color space has been abandoned. The distance difference is not correct. And the color testing sample, we cannot reproduce right now. So every step has big problem. But the people has learned how to use this kind of index. So even during the past 10 years, around 10 years, many people create a new index, try to persuade people, say the new index has more exactly describe the quality of that. But no one liked the new one because we don't like to pay another effort to learn how good the index is. Okay, we know CI 80 is what kind of quality it is, but when we use the new index, we don't know the index till 80 how good it is, 85 how good it is. We don't know. We need pay more effort to learn. So people don't like it. New index. It is try to calculate, evaluate the color fidelity. What's the fidelity? Means how like to each other. Okay, how similar to each other. Fidelity. Okay, so this kind of index designed to test, to evaluate the color fidelity. So how to calculate? Very similar to our previous CI. Our testing source, light source, so we should measure the power spectrum distribution. And we have a reference or standard light source. So how to choose the standard light source for the comparison with the same CCT, okay, with the same CCT. So we must measure the power spectrum, and the power spectrum, based on the power spectrum, we calculate the corresponding color coordinate. And with the color coordinate, we can calculate each CCT, and we choose the same CCT to have the reference, corresponding reference light source. Okay, so we have two spectrum. And for measurement people or standard metric people, they are worried about how can I have this kind of reference illuminance? How can I have that? Because it is not related to just A or D series light source. They are worried about if right now we have a source 1 with CCT, for example, 2,000 and 500K. So we should prepare, for example, the daylight source with 2,000 and 500K. Next example, next example, we have a 2,000 and 600K. Then we should prepare another light source with 2,000 and 600K. So it means you must prepare infinite number of reference light sources. So it is not practical. We cannot prepare so many standardized sources for this kind of measurement comparison. So we just can calculate by calculation, cannot by real measurement. Okay? So we have a two spectrum, light source, and we have a color sample. In this proposal, they criticize why we just choose 8 colors, and previously 8 colors are unsaturated color. So it is not fair to some saturated light source. So they prepare 100 color samples. Okay, 100 color samples. So right now you can have a 2 set of light source and test on 100 color sample. So you have a calculated color coordinate. How many the number? 100 times 200 color coordinate. So you have a 100 color difference, and they adapt new color space, and use the color appearance model. What is the color appearance model? We currently we just transform one light spectrum into one color coordinate, right? So this is point to point. But for human eye, our human vision, we see not point by point. We see a whole picture in one time. Okay? So you must calculate your feeling. When you see 2 colors is the same or not, we compare the whole picture. So the color appearance model tell you one color, how will it perceive into the another color in the another background. So there is a new transformation. So this is the mechanical colors and transfer into the human vision colors. So XYZ become JMH. JMH means brightness, saturation, and hue. Okay, this is talking about human perception. This is talking about machine detection. There is additional transformation trying to describe how your brain to identify the colors. So we calculated the color difference in this new space. Okay. So again, average the color difference and receive the transform the color new space and calculate color difference in that new space based on human perception, not just machine detection. Then average over all the sample. So average over the sample. Again, the average is not just a simple average, it is Loomis square average. Okay? So they remove one suburb. Previously, the CI can be negative. When your color difference big enough, your CI will become negative. So it is not so, it feels so good. So they use the Loomis square. So the average color difference will never go to negative. Okay, never go to negative. And they might have a bad, not so good mathematical skill. So they design not so good looking transformation to do the scaling. So they define this transformation to have a new index. Okay. So this kind of proposal is not just only one. And at the final decision, they didn't pass the voting. So this proposal never become an international standard. So I just tell you, our simple idea can be implemented to real method procedure, but you still need to more consider the procedure is good enough, and you need pay more effort to learn this new index. Okay. Okay, I talked too much. This kind of color fidelity. So we calculated the color difference. There are many other methods to calculate based on the preference. You not just test by the spectrum calculation, just tested by do you like it or not. So you just look at the sample, color sample, and evaluate, give it a score, 10 or 8 or 5. How good or do you like it or not? So give it a score to change, to calculate. So some index is based on preference, not fidelity. Okay? So there are several other methods. So many kind of methods has been discussed during the past 20 years. And finally, no one become the standard. So finally, people accept another new. Okay, I have no time talk today. I try to finish here. You can see fidelity based on calculate color difference. Preference we calculate the visual clarity, discrimination, or category color, or harmony. Okay. One small joke. When talking about the discussion, the index, especially for the preference. So one designer say we test to see the color rate is similar to your memory rate or not. So they use the apple to let the tester to see the apple is rated good enough or not, or no. The other one Japanese raised his hand say, in our country, our apple are in green, never in red. So we have a memory about red apple. So how to test the memory color? Okay, so every method has their own advantage and their disadvantage. Okay, so I just tell you the history in the past 10 years. Many kind of methods try to solve some problem, but create another new problem. Okay, so finally we have another new solution to try to solve the CRI problem. But even so many effort has been paid, currently the new method is not so popular. People need to pay more effort to learn how to see, how to use this kind of new index. Okay. Don't worry about the exam on this kind of calculation. You just need to learn how to use this kind of concept to evaluate light source, then it's good enough. Okay? Because the calculation is tedious, is troublesome, and it's not easy to do by hand. So you just learn the concept and possibly do a problem, then it's good enough. Okay? Okay, sorry I take too long time. Today we stop here. And next week we